let's see if we can make the definition of the limit of f of x as x approaches a equals L. Let's see if we can make that definition a little bit more precise. To do that, let's start with an interval of values around L. So let's say that L is at the center of this interval, and the distance from the center, L, to the upper bound or the lower bound on that interval is epsilon. So that the upper bound, the height of that parenthesis would be at L plus epsilon. The height of the lower bound is at L minus epsilon. And if you recall, the informal definition of limit is that, okay, as x gets closer and closer to a, f of x should get closer and closer to L. Well, here's how we can define how close we need to be to a to get within, say, epsilon of L. All we have to do is create an epsilon band around L. So what do I mean by that? Well, go out horizontally from the lower bound height till you intersect the function, and then go out horizontally from the upper bound height until you intersect the function. And then go down vertically from those intersection values. And look at the shorter distance between where the vertical lines in green intersect the x-axis and a. The shorter distance would, at least the way I've drawn it here, it looks like the shorter distance would be this distance. And let's call that distance delta. So let's call that delta. And so the idea then is if you create a corresponding interval that has a radius of length delta, so that I'm going to say that that distance is also delta, so that this endpoint is a plus delta, and this endpoint is at a minus delta. And then the idea is if you pick an x value in this interval, say here, then certainly f of x will be within epsilon of L. So now that we've grabbed hold of some actual values, the epsilon, the delta, the A, the L, now that we've grabbed hold of some actual values, we can make this definition, this Calc 1 definition of limit, much more precise. That picture leads to the Epsilon-Delta definition of limit from Calculus 1. Okay, assumptions. Let's assume y equals f of x is defined on an interval I, an open interval I. Say it has endpoints x1 and x2, for instance. So, okay, I'll say I is an open interval containing A. So y equals f of x is defined on I, an open interval containing A. Now, y equals f of x may not be defined at A itself. So we'll say, except possibly at x equals A. Y equals f of x is defined on I, except possibly at A. Okay, so here's the definition. We'll say this: the limit of f of x as x approaches A is equal to L if for all epsilon greater than 0, there is a delta greater than 0 such that, so delta is a number, epsilon's a number, delta greater than 0 such that the distance between f of x and L, we could write that as the absolute value of fx minus L, is less than epsilon whenever the distance between x and a, we could write that as the absolute value of x minus a, whenever that distance is less than delta. But not equal to 0, so we'll say greater than 0. So the distance x minus a is going to be bigger than 0. It's in between 0 and delta, let's say. So this is just a formal way of saying what the picture that we just got done talking about says. You give me an epsilon, then there is a delta such that we can get the distance between f of x and L less than epsilon as long as x is within delta of a, but not equal to a itself. As long as all that's true, then this limit is going to exist. And again, that's just a formal way of saying, hey, the closer x gets to a, at least eventually, the closer x gets to a, eventually the closer f of x gets to L.